thanks very much. I apologize in advance for some of the slightly unprepared nature of this talk. Please ignore the column over there. It has nothing to do with this talk. So I want to talk a little bit about the Abel-Jacobi map and mirror symmetry for open strings. And this is based on work in progress of mine with Hans Jokers and Johannes Walscher. And the basic point is described here in the abstract. If I have a boundary condition for open strings, which takes the form of some homologically trivial cycle, whose Abel-Jacobi mapping is non-trivial, how can I predict the special Lagrangian cycle in the mirror, which provides the mirror boundary condition? Just to kind of get started, mirror symmetry is something which has been around for a long time, and one of the features of mirror symmetry, as we know it, is an association between algebraic cycles on a given Calabi-Yau threefold with second cohomology classes on a mirror variety of the original variety X. This extends in a way to open mirror symmetry because the algebraic cycles serve as boundary conditions for open B-branes, while the second cohomology classes serve as boundary conditions for open A-branes. And so it would be desirable to have a kind of algorithmic method for starting with some boundary condition expressed in terms of B-branes and write down the associated boundary condition in terms of A-branes. So we don't have an answer to this yet, but we do have some really interesting examples. I've given versions of this talk before. I gave one in Miami in January and in Urbana last July, and if you heard either of those, I do apologize for the repetition. I'll also describe a little bit of work that I'm doing at present with Sheldon Katz, which was motivated by some work that Vafa and his collaborators are doing, which I think will be featured in the talk that he gives in a couple of days. So to get started, I want to talk about the quintic threefold and its mirror, and I'll just briefly sort of switch, if I can, to something. That's completely not what I'm trying to switch to. So I'm trying to switch to this work that I described where we managed to describe the entire 101 parameter family of the mirror quintic threefold. So I'd like to just briefly describe what Sheldon and I have learned about the 101 parameter family. So this family has been around for a long time. The family is usually described as the quintic itself modulo a group action, an appropriate quintic modulo of the group action, one which is invariant under the group. So if I take the quintic equation of that form, the sum of the fifth powers is equal to a constant times the product of the variables. Then there is a natural coordinate-wise action of z phi to the fourth on that, in which the diagonal subgroup acts trivially on P4. So that's an effective action of z phi q. And the way that we use to describe the set of possible divisors on this is to actually first do the group theory and figure out what the invariants of z phi to the fourth are. And I think I have that displayed next before paragraph. So we've got the group action acting on various pieces of this thing, and eventually, we describe the entire quotient as a sum of 5 variables is equal to a constant times one of the variables, and the product of the 5 variables is equal to a fifth power. So that's a singular quintic in P5, invariance under the Z5 cube action. It has singularities, and the singularities are located along 10 lines. And then there are worse singularities at the vanishing of 3 of these coordinates, VW, X, Y, and Z, the vanishing of 3 of them instead of 2. And there are also 10 of those points. So this particular description of the mirror quintic is implicit in some of the existing literature. And given it, you can describe the resolution of the codimension 3 singular points in terms of a honeycomb diagram like this, in which the divisors are labeled by monomials in the original variable. That labeling gives us a way to describe possible curves. Curves are described as intersections of divisors, pairs of divisors, and so 2 labels which have an adjacency in the honeycomb diagram will end up describing an appropriate curve. In addition, we have curves which are lines in the P2s on the thing, and some curves which are associated with the resolution of the one-dimensional singular locus, these sigma STs, which are sections of appropriate one-dimensional singular locus. And our result is that each of those 215 curves that I've just described are exceptional curves for the mirror quintic. They're exceptional in the sense of Mori, so they form edges of the Mori cone, and we conjecture that that set of edges of the Mori cone is a complete set of edges of the Mori cone. So we've got control, we think, over all 115 parameters, all 101 parameters that are involved in the description of the mirror quintic. So that's a good place to get going with the study of the mirror quintic. But what I really want to do is talk about some other classes in the mirror quintic, some ones which have had interesting open string invariants associated with them. And for the purpose of describing those other classes, I'm going to switch to the document camera. Basic points to start with the mirror quintic, which I'm writing in a form of x, y, q. And that mirror quintic contains various 2 cycles. And the way I'm going to exploit those 2 cycles is to use the Card-Fuchs operator. And the Card-Fuchs operator will have a property that, if it is applied to any of the periods of the holomorphic 3 form on the quintic, it gives 0. So I start out with periods which vanish under application of the Card-Fuchs operator, and then I take open string states say gamma tilde, which correspond to cases where the open cycles can end. And I apply the Card-Fuchs operator to gamma tilde. Equals 0. Thank you. Apparently, I was not audible during that, so I'll describe again. To go through the thing that Walsher, Jokers, and I are trying to do, I start with the mirror quintic x mod z5 cube that contains certain 2 cycles. If I start with an ordinary 2 cycle on the mirror quintic and apply the Card-Fuchs operator to the integral of that, excuse me, if I start with an ordinary 3 cycle gamma on the mirror quintic, apply that Card-Fuchs operator to the integral over gamma of the holomorphic 3 form, I get 0. But if I apply the same Card-Fuchs operator to an integral over a gamma tilde, which is the boundary of an open string state, I typically don't get 0 as a result of applying that. And typically, the result of applying the Picard-Fuchs operator to an integral like that, an inhomogeneous solution of the Picard-Fuchs equation, lies in some extension of Q, finite extension of Q. And the goal of our project is to understand something about the number theory of the corresponding extension, and also how to generate geometrically the corresponding mirror cycles to the original cycle. So the way that I'm getting a cycle of this kind, this goes back to work that I did with Vulture around 2006. So sort of harks back to Morrison Vulture 2006. In that case, the cycle that we used was a two-cycle, which took the form of the difference of two conics, C plus minus C minus. And what we learned was that the Picard-Fuchs operator applied to C plus, the integral of omega over C plus minus C minus, was in some sort of quadratic extension of Q. And given a Picard-Fuchs operator like that, we were then able to guess what the corresponding mirror cycle was. So this led to an identification of the mirror cycle. The mirror cycle should be a special Lagrangian on the mirror Calabi-Yau threefold. And when we looked at this problem in 2006, the only special Lagrangians we knew were the ones that came from Bryant's construction, where you look at the set of real points on a real Calabi-Yau. And we successfully identified this difference of two conics, C plus minus C minus, thought of as the boundary conditions for open strings on the mirror quintic, with the real locus of the quintic, when the quintic itself was defined as real. So the real locus of the quintic contained within the quintic as the mirror of the story that we had for the quintic mirror. What we're trying to do more recently, and in collaboration with Jokers, is to study a different case where we look instead of the these are called Deligne conics sometimes. These particular conics that exist on the mirror quintic were written down by Deligne, who noticed that certain hyperplane sections of the quintic had to be reducible into a pair of conics together with a line. Another interesting class of cycles on threefolds is given by the von Neumann lines. The von Neumann lines were written down first by von Neumann, but were published by Albano and Katz. And they're a particular infinite family of lines on the mirror quintic. You obtain these von Neumann lines by starting with the standard equation of the mirror quintic, which looks like this. The sum of the fifth powers minus a constant times the product of the variables is equal to 0. And you essentially impose certain vanishing to get lines of the form xi equals lambda xj. And you look for lines of that sort, and you find that there are such lines of that sort, and that when you can discuss such lines, you can then make some calculation of what the Picard-Fuchs operator is going to be like on the difference of two von Neumann lines. So this was the first calculation that we made. We integrated the holomorphic three-form over the difference of these two von Neumann lines and applied the Picard-Fuchs operator and got some interesting element of a number field. want to do more. We want to actually find the corresponding open string boundary conditions. And in order to do that, we investigated a little bit further. We investigated an extension, extended the Picard-Fuchs operator to the following situation. So the Picard-Fuchs operator would normally have gone from the periods of three forms and produce some sort of number, complex numbers, out of periods of three forms. But this Picard-Fuchs operator can be extended in some very natural way to a sort of Chow group, or more precisely, higher Chow groups of cycles. So that we ended up with a higher Chow group of a mirror quintic mapping to, by means of a Picard-Fuchs type operation, mapping to an appropriate target space for higher Chow groups. Those target spaces are essentially regulators in K-theory. And we're able to make a calculation for the particular class of differences of von Neumann lines into a particular regulator of K-theory. So the actual calculation involves some interesting quantities. They're the same quantities which appear in the construction of hyperbolic three manifolds. So through a calculational procedure, we established a relationship between appropriate algebraic cycles on the mirror quintic. I should say that these cycles can have their class calculated in the more recent work that Katz and I did to figure out all the possible cycle classes. But we worked out a relationship between the quantities that were appearing in these higher Chow group calculations, which refine the period calculation, and some things which appear in the construction of hyperbolic three manifolds directly. So this is work of Walter Neumann and Gonzague to see how the hyperbolic volumes of the hyperbolic three manifolds are determined by this kind of calculation. So that has led us to speculate on possible mirrors. So what mirrors could there be? What we want is a special Lagrangian cycle in the quintic itself. That's the kind of thing that we're expecting to see as the mirror of some explicit algebraic cycle on the quintic mirror, which would define an appropriate set of open string boundary conditions. And how would we get such a cycle? Well, we would need a three cycle, a gamma 3, embedded in the quintic mirror, which is a six manifold. And what's more natural to conjecture than that, or conjecture, or possibly guess, is that the volume of the three cycle, which we need to produce the mirror construction, is equal to the Neumann-Zagier volume. Associated to the Picard-Fuchs calculation of the mirror cycle. So we start out with the von Neumann lines. We make a calculation of what the behavior is of the higher child groups in that particular case. We can do this similar thing for a finite collection of other examples as well, I should mention, where we're led to a natural extension of the usual Picard-Fuchs calculus into volume of a